Okay, so good. So far we are on the last section of particle kinematics. So we have covered everything we're covering in chapter 2. I will discuss today absolute dependent motion, which closes this out. One of the things to realize with this particular chapter is that we cover a great deal of information. At no other point in this course will we cover as many ideas simultaneously and as quickly. So, where we start here is we have two particles that are connected by a cord. Mass A is connected to the cord at one end. It goes around a pulley, and at the pulley there's two points of contact that are of interest, C and D, and then it goes to mass B. And we can write this distance as S sub A and S sub B. So the trick here with all of this stuff is to define the total length of that cord. And so if I look at that, I can say that the total length of the cord is equal to S sub A plus S sub B plus the length C to D. And I'm using different variables for time varying constants. So as B slides down the ramp and A goes up the ramp, SA and SB will change in length. LCD, on the other case, will never change. So that's going to be a constant length. So you have variable lengths, you have constant lengths that are sort of playing a role in this. And the obvious thing to do is move the Grammarly thing. Just move it out there. Is to take a derivative. What is, oh, okay. So I can say SA plus SB is equal to length total minus length C sub D. Take the derivatives, SA dot plus SB dot equals to 0. Because the constant dLT dt, dLCD dt is equal to 0. And so the only term that's left is dSA dt and dSB dt. Now this is where it gets a little bit funny. So, please stop this. Why did it do that? There we go. It hates me. All right. Not to worry. God, it just doesn't want to do it today. Anyways, I'm going to make this worse for myself, and I'm just going to move this over here. Come on. Okay, sorry, just, ugh. All right, I'm just going to rewrite this over here. SA dot plus SB dot is equal to 0. SA dot equals to minus SB dot, which tells you VA equals minus VB, and acceleration of A equals acceleration of B. Which is not a surprise if you're looking at the right figure. Oh, there we go, finally. Right there. Okay. So really tiny script. But what this is really telling you is not the acceleration. It is not telling you the velocity. It's telling you the rate of change of length. So if A is increasing in length, B is decreasing in length. If you're looking at the rate of change of length, that's your acceleration. So you have to be very careful because you often have situations where things are moving up a ramp and the length is decreasing, and down a ramp and the length is increasing. And so you have to be very careful with your axes and how you define things. Which leads to this problem right here. Now this is kind of a straightforward problem in the sense that there's not much happening in terms of weird sort of coordinates. But here I have more pulleys. Now here are two standard pulleys that you're used to, E and C. They are fixed in position and will not move during any type of motion that occurs on the block B. However, block A can move. And so block A will change in length. So we could sort of define here a length C, SA, SA, and a length A here, length C, length C2, I'm going to call that. I have H, which is going to be a fixed distance, and I finally have S sub B over here. So I can and will, at this point in the course, start to talk about pulley lengths and include them in these calculations. But later on, you forget about them because they're constants. So this distance here, A, C, and E, are constant lengths as far as my calculations are concerned. The only thing that changes are the lengths SA and SB. So if I want the total length of this thing, that's going to equal length of all the pulleys plus SA plus SA plus H, which is that height between C and E, but that doesn't change, plus SB equals to length total. Again, as I'm solving these, well, oh, sorry, it's length total equals length total. So it's the same thing on both sides. There. This term is constant, this term is constant, that term is constant. So I can bring all of that to the left-hand side. Length total minus length of pulleys. And length of pulleys is A, C, and E. Equals to, oh no, minus H is equal to 2SA plus SB. So as I'm calculating all of this, I'm bringing all of the constant terms to one side, taking the derivatives, and when I take the derivative of this term on the left-hand side goes to 0. So 0 equals to 2 SA dot plus SB dot. And this ends up being that problem. You really, really want this to make sense. And every time you look at it mathematically, it just drives you batty. Okay, so 2 SA dot plus SB dot is really 2 SA dot equals minus SB dot. So you can define coordinate systems here where you have two cases where the acceleration is increasing. Say, for example, if you just use the xy coordinate system there, if b is going at higher velocities and moving to the right, a is moving upwards. Both of those are positive according to that coordinate system. But your calculation is giving you a negative number. So you have to realize what the motion is as much as you have to realize what you're dealing with in these figures. Oh, I'm not going to try these. Okay. There we go. All right. Things get more complex. So don't expect to always have a nice problem with one cord wrapped around another. You're going to have multiple wraps on a cord. So here, for example, you have one pulley and another pulley. So here you have one pulley, and then over on the other side here, you have another cord. And you can see they're not attached to each other. So you still have to come up with relationships one to the other while they're attached through D. But what do you do? You end up with these kinds of relationships. So if you look first of all at the pulley A, you can take the cord of that wraps around pulley A, and you can say, well, it has a length y sub A, which is the first part, and let me just see if I don't do this wrong. You have y sub A here, you have y sub D here, you have y sub D here, and you'll notice that I've kind of eliminated that constant length already. I'm not worried about it because it's not going to play a role in my derivatives. So length of A is equal to YA plus two YD. I can zoom it out a little bit. The next one, the lines in purple, I'm going to have to look, and it's not YA, it's YB there. I have YB plus YC plus YC minus YD. And that's how I bridge between pulleys. This is going to be a lot of work that you do in this course. You're going to have examples of this sort that you have to deal with. But it's useful to recognize how you do the bridging between pulleys as much as the bridging along one pulley. So wraparound lengths, straightforward, they're not bad. But writing these sorts of relationships, the first time you do it, it is really confusing. After a while, it gets better, it gets better. It takes a while to sort of get through all of that. So, as you take the derivative of that, you get rid of all those constant terms. And you can see why, as I'm writing this, I'm going to get lazy and I'm going to forget about the constant terms because they're not important. But now I have a relationship between the change in length of A and the change in length of D. But I also now have a relationship between the change in length of B, C, and D. So I'll be given something along the lines of, I've got a pulley going down with a velocity, or a mass going down with a velocity of 10 meters per second, and have to solve for everything else. And everything else will be related by these pulley relationships. In the next chapter, which starts tomorrow, we'll talk about cases where you solve for the forces, calculate the accelerations, and use these types of pulley relationships again. Any questions on this?
So when you say bridge the two pulleys, that just means relate a value so you can relate the derivative?
Exactly. So you want to relate that length that's associated with these yellow lines with these purple lines. Because one of the problems you have is you cannot say, for example, YB plus YC plus YC plus YD plus YD plus YA. Because they're not the same chord, they don't align, and the relationship is not there. But you can say the chord that goes from B to point D is one chord. The second chord from the top to point A is a second chord. And you have to somehow come across, and the bridging is at point D. Any other questions on this? The really important point here is you're really not calculating velocities, you're not calculating acceleration, you're calculating the rate of change of length or the rate of change of the rate of change of length. So that's the important thing to understand, because otherwise it makes no sense at all. These velocities don't really make me happy. Let's try a simpler one. Okay. So I have multiple pulleys. So this is not, it's not a case of compound pulleys where I have one pulley attached to another. I have one cord wrapped all the way around that goes from point A to point B. Now, a couple things you should always notice in all of these drawings is what are the fixed points, and the fixed points are C and E. This expertly drawn slider at point D tells you that D moves up and down. And so it's not going to be a fixed length. And as you calculate things, you're going to have to know where everything is relative to each other. Pulley D is attached to a collar which is pulled down at 7.5 meters per second. Centimeters per second, excuse me. At time equals 0, collar A starts moving down from k with constant acceleration and 0 initial velocity. Knowing that the velocity of collar A is 30 centimeters per second as it passes point L, determine the change in elevation, velocity, and acceleration of block B when block A is at L. Perfectly obvious, right? So all that's happened is I've dropped A from K to L, and I want to know what's going on with B. So intuitively, what I expect to have happen is that B is going to move up. And I just have to figure out if it does, or it might get a little bit weird and D might move down and everything change from what I expect. So D is going to make things a little bit weird. Don't go anywhere. Yeah. All right, so I have an origin that starts at the very top. It's where the ceiling is attached. I have K to L over there, and I have a velocity of 30 centimeters per second at that point. So velocity of A is given, acceleration of A is constant. That's the only thing I know. So this is a constant acceleration problem. I have the distances traveled, and I have the velocities. So v squared, so I can use the relationship which comes out of acceleration equals v dv dx. In this case, again, there's no need to rederive relationships that you already know. So a constant acceleration expression does not have to be rederived on a quiz, an exam, or a homework. You just use this relationship and say, yes, this is constant acceleration. So VA squared equals VA naught squared plus twice acceleration A, XA minus XA naught. Now I've defined positive downward, so that works out. So it's displaced by 20 centimeters. And you'll notice that I've when I've written this in units. So I have the units with my numbers to help me so that I remember and I don't end up doing the typical thing which I do, which is rewrite this as meters per second later. So writing down the units helps me remember all of this stuff, and I can see right away that I'll have centimeters per second squared as an answer. So if I solve through for that, I'll have the acceleration just calculate 30 squared divided by 20 divided by 2 divided by 40 in the end. I'll end up with 22.5 centimeters per second squared. Now, if I then take that acceleration, put it in, calculate the time, I will get the time it took to go from K to L, which is 1.33 seconds. So the other thing that I want, I'm given that D is moving down at 7.5 centimeters per second, XD naught, XD, I don't know how far they've gone. So XD equals XD naught plus velocity of d times time, and delta xd is equal to 7.5 centimeters times 1.33 seconds, which is equal to 10 centimeters if you don't worry about your significant figures. So I have the displacement now. So I took the information I got in the first part, I took that time, and I know that's the same amount of time it takes for the block D to displace. So, and I didn't write that correctly. And I can tell I didn't write it correctly because I didn't get the right units. So again, the most obvious sort of helpful thing as you're studying for the quizzes, as you're studying for everything that's coming up, write your units. And when you make a mistake, it'll be obvious because you'll see that the units can't make sense. Or if they, or you can catch them like I just did and realize that you didn't put a seconds in there. So if I look at the total length of that cable, so if I take this cable, go here, wrap around the pulley, go here, wrap around the pulley, go here, wrap around the pulley, come down to here, I have a total length that again is going to be a constant length. And hopefully all the information is there. I can say that's equal to XA plus twice XD plus XB, which equals a constant. Velocity of A equals to plus twice velocity of D plus velocity of B is equal to 0. Okay. And this is where it gets a little bit funny because what's happening here is that one, I have a positive or an increasing length for A and I have an increasing length for D. And, oh, yeah, all right. 30 centimeters per second plus 2 times 7.5 centimeters per second plus V sub B is equal to 0. And V sub B is equal to 45 centimeters per second. So that's the magnitude. B is moving up. In order for B, or for the chord to remain a constant length, and both A and D to drop, B has to be going upwards. Otherwise, it makes no sense. And acceleration of B is still going upwards. I kind of wrote it this way. You're not, one of the problems here is that you're not really solving, maybe I should leave it as negative for both. That probably would make more sense later. Again, you're not solving for velocities. You're solving for the change in length. And so this is the rate of change of the length. It's decreasing by 45 centimeters per second. And this is the rate of change of the rate of change of length, which is minus 22.5 centimeters per second squared. So again, kind of intuitively, B is shrinking. As A and D increase in length, B has to decrease. Any questions on that one? Go ahead.
Why is AD equal to 0?
Oh, it's constant. You were told at the beginning of the problem that the velocity of D is a constant velocity, and it's dropping at that rate. Go ahead. This is where intuition fails. Intuitively, what you want, what I want, when I look at a problem like this, is that A and B drop and D rises. That's the intuitive approach or intuitive answer to this. But an equally valid answer, when you know it moves from here to here on A, and you know it's moving downwards on D, is that this has to be moving upwards. And we will look at cases where the forces drive this motion. And it's one of the reasons why I throw away all of your intuition about what's happening. Don't go in there with the assumption that this will happen. Just take what the numbers give you. And it's also why it's really important that you look at the rate of change of length when you solve these problems. If it's increasing in length, you know it's going down. If it's decreasing in length, it's going up. Go ahead.
So if we weren't given the velocity or acceleration for D, we wouldn't be able to solve.
No, you wouldn't. It would be a different problem, and we would give you something else. So you will see problems of this nature, but it'll be sort of worked out with enough information you can figure everything out from there. Any other questions?
Yeah, how did you get 2xd? Like I said xa plus.
So you have C here, D here, and B here.
All because of 2.
Yeah, because of wraparound. And so this is also part of this. This is kind of interesting right now, but it's really more interesting when we deal with Chapter 3 problems, because the reason why you wrap around a pulley like this is the force in the pulley stays the same. And so force is constant throughout there. So if you have a wraparound here, you have twice the force and half the displacement. And you're going to see that over and over with multi sort of wraps of pulleys. Okay. Any other questions on this one? These are the types of questions you've got to do on your own. You don't have to do this. This is not covered on the quiz, just so you remember. But it's just something that's useful to sort of look at later. So typically when you look at these pulley problems, you have a pulley that wraps around and it goes either up or down or left or right. Infrequently you'll see problems where you have an angle associated with one of the chords. But calculating everything still requires you to know what's happening in terms of the rate of change of length. Oh, okay. Sorry, I actually should read the question. Tractor A is used to hoist the bale B with the pulley. Arrangement shown. If A has a forward velocity, V sub A, determine an expression for the upward velocity V sub B of the bale in terms of x. And x is that distance that the tractor is displacing to the right. So the total length of this cord is going to be the wraparound length here, here, and the total length over here, which is L. So I can write that as twice h minus y plus L. But L is not everything that I have there. So h is constant, so I know that. So as the tractor moves to the right, x is going to change, but h is not. So that is equal to L equals 2h minus y plus h squared plus x squared to the 1/2. So you can see where the problem is. The problem is that with this particular case, I'm going to have a derivative, and it'll end up being slightly more complex than the other derivatives I got in the previous example. So 0 is equal to minus 2 y dot plus x dot over h squared plus x squared. Yep, that's good. So even though it's just a straight length, I can't just say L plus h minus y times 2. I have to go through and calculate the actual distance of h, or L, and leave it in that form up there. So when I take the derivative with respect to time, I end up with this. And this one works out really nicely, because I get y dot equals to 1/2 x VA h squared plus x squared to the 1/2. Okay. And the nice thing about this is, in the coordinate system I have, x is positive to the right, y is positive upwards, and so increasing v sub a is increasing v sub y. And so when you're looking at these problems and you're solving through for all of these things, remember that's what you're dealing with. And also, that differentiation is something that's pretty straightforward and one you should be familiar with at this point, and just be a little bit comfortable. It's not as complex as, say, a tan or ln. Okay. Any questions on that?
So the question says VB in terms of x. So when it says VA,
Oh, okay.
will we leave that x dot or something?
Yeah, I probably should have written this a little bit differently, but VA is here, VB is here, y dot equals v sub b, and x dot equals v sub a. So those, and that's one of the problems with this, okay, because you're looking at a problem and I'm saying, okay, look, this is the rate of change of length. Now the rate of change of length is directly the same as the velocity of point A, but it could be left or right depending on the problem. I've chosen a coordinate system in this particular case that worked out to my advantage in the sense that both of those are positive. So the xy that I have are both positive upwards and positive to the right. So even though B is decreasing in length as A increases in length, or X is increasing in length, Y is increasing in length too. That's a funny thing. There you go. You could have solved it another way. You could have solved it with a coordinate system, and this is something to try on your own, where you have x and y like this. And you would then have y minus h, where you put the h with, you would flip it around, and in that case, this would be y, or this would be, yeah, this would just be y. So it would all be in terms of y. So you start at the big Y, which is equal to h at the bottom, and it goes to y equals 0 at the top. Then you'll get the same result, but it'll be negative. Coordinate systems matter. Coordinate systems matter a whole lot for everything we've done up to this point. So how you define the coordinate system, where you define your origin, where you define everything with respect to is going to be crucial. All right. Voila. Okay. So another problem that you might deal with is something like this. So this is like the first one, which was that compound pulley. This is it's called a compound Atwood machine. Not related to Margaret Atwood, but you're asked to calculate velocity of A and acceleration of A. So you're given a pulley mass A, which is attached to the pulley D. Pulley D has on it two masses, B and C. Oh, good for me. So I can relate everything to another position. So in this case, and this is where sort of these, looking at these things this way is important. I have XA. I've defined XD with respect to E. I have XB, and I have XC. So XA plus XD equals length 1. XB plus XC is equal to length 2. Right. So I have there two lengths, and maybe I should have called it something else, but it's okay. So XB, XC, XCD, XA. Okay, great. So I can go XA dot plus XD dot is equal to velocity of A plus velocity of D, which is equal to 0. Those are both constants. Those are the lengths. They all sort of work out really nicely in that case. Okay. Next one. So if I do that for B and C, I just have x dot B plus x dot C is equal to 0, x dot double dot B plus x double dot C equal to 0, and all of it sort of continues. But I can also say, look, oh, good. There. I can say xb1 is equal to xd plus xb. And I'm just adding the 2 points together and referencing it to point E. So D is changing, B is changing. So xb1 is just reference to this upper origin. And that's how I'm going to, again, bridge between the two pulleys and say, well, xb1 is equal to the total length from that origin at point D. I can define any origin I want. I just need to take into consideration that D is moving. And if D is moving, I can calculate it in terms of VB1. And I can do the same for C. And if I do that, I end up with now a relationship that allows me to use the information from velocity and acceleration at point D. Go ahead.
For the first derivative of xb1, is it supposed to be x?
It should be xb, or x dot b. Okay. There's not much else to talk about on that particular problem. I just want to see how long I have. Questions? This is easy in lecture. It's really hard to do. Just sort of a warning about it. You're going to spend a lot of time looking at it, and it's really important to draw out those lengths and make sure you're comfortable with them, particularly, and I'm not going to do it, when you, oh, it's not there. When you have questions like this. And since I don't have time to do it, I can give you the answer to this. I'll give you the problem with the lecture. I am not going to work out the problem, and hopefully if I do this right and I turn around in enough time, you should get all 8 lectures for particle kinematics today. So I'll have the OneNote out, and it should be out later today. Any questions on this? I know you're very excited to go out into the sun. Yeah.
When you made the first equation where the xb1 equals xd plus xb, the first line, how did you do that for xd is not
So that length is changing. So when I did the initial thing, I just said A plus D, B plus C. So I have a relationship between each of those pulley velocities. But I can reference a changing length and add it into this. All I'm doing is changing the origin. And the origin in the second part is up here. And it's made up of x sub d and x sub c.